In today's note, we're going to be looking at chemical families. So basically, we're going to be looking at some of the different groups in the periodic table and how the elements in those groups have similarities, and then how they kind of relate to each other. So our first group that we're going to look at are the alkali metals. So that is group number 1. We can see, looking at a periodic table, that is lithium, sodium, potassium, rubidium, cesium, and francium. We're really going to be mostly focusing again on the elements from 1 to 20, so from hydrogen to calcium. So for in this course, so that is really just focusing on lithium, sodium, potassium. For their appearance, alkali metals are silvery colored metals. They're soft, and they can be easily cut with a knife to expose a shiny surface which dulls on oxidation. So this is basically what your alkali metals look like. You can see that silvery color. We can see lithium, sodium, potassium. They all look pretty much the same. Generally that grayish color. There is some luster to them. For the alkali metals, for their general reactivity, they are highly reactive, and we'll look a little bit later at why they're reactive and in other notes, but the alkali metals are highly reactive. And the reactivity increases as you go down the group. So if we're looking at the top of the group, we're looking at lithium all the way down to francium. Francium is the most reactive and lithium is the least reactive. So that is just out of the group. Overall, they are still very highly reactive compared to other elements. But in terms of their group, the most reactive is at the bottom. And again, we'll look at a reason why later. Because they're so highly reactive, they're usually stored in a mineral oil or kerosene. That's because they're so reactive that they will react with kind of the oxygen in the air or the water vapors in air itself. They will react to that. And you can find videos on YouTube of how reactive they actually are with water. Their occurrence and extraction. So again, because we've talked about how highly reactive they are, these elements are too reactive to be found kind of free floating in nature. So you're not going to find like a pile of lithium lying on the ground somewhere, just because it's so reactive that it wouldn't be able to be stable and be found in nature. It would react, so you wouldn't be able to actually find it. Some of the physical properties of the alkali metals, they do differ from other metals that you will see in the periodic table. Some of the more common ones that you might think of, like gold, silver, platinum, and aluminum, stuff like that. They are soft. They have a low melting and boiling point. They have low densities, and they do tend to tarnish. So they are different from other metals in those aspects. Looking at the Bohr-Rutherford diagrams, and again, you may have noticed this in previous notes or activities, but if you look at the Bohr-Rutherford diagrams for at least the 3 elements that we're going to be focusing on in the top 20, lithium, sodium, and potassium, and again, this would be the same for the other ones as well. If you look at the electrons, there is 1 electron in the outer shell. And that's going to be common for everything in group 1. There's always going to be 1 electron in the outer shell. And this is part of what makes it highly reactive, because that 1 electron, there's not going to be a lot of energy required to pull that 1 electron away from the atom. We'll talk about ions and compounds in a later note, but to pull 1 electron away, there's not that much energy required. So these elements would be highly reactive, because again, it doesn't take that much energy to force a reaction. Now, the reason why, as we go down, is so as we go from lithium down to sodium, down to potassium, and so on, the reason they get more reactive, even though they all have 1 electron in their outer shell. If you look at potassium compared to lithium, there are multiple shells involved. Whereas lithium only has 2 shells, potassium has 4 shells. So that electron all the way out there in that outermost shell, it's far away from that positive core. So it's going to require even less energy to pull that 1 electron away. And we'll talk again in other notes about why you would want to pull that one electron away. But you could think of it, if you have two magnets that are close together, they're going to be more attracted, and it's going to be harder to pull them apart, especially if they're touching. But if you hold the magnets farther and farther away, then it will be harder. It will be easier, to separate them. So again, that's why the larger or the more shells or the more electrons it has, the easier it is to pull that last electron off, which makes it part of a reason of why it's highly reactive. Group 2 are alkaline earth metals. So this is the second column in the periodic table. So looking at beryllium, magnesium, calcium, strontium, barium, and radium. Again, we're only looking at the first 20, so really just the first 3 in this group. Beryllium, magnesium, and calcium are the ones we're concerned about. In terms of their appearance, the alkaline earth metals, they are metals as they go by their name. They are shiny and they're a silvery white color. So these are the 3 main ones that we're looking at. You can see again the metal or the metallic appearance. We can see the luster, they are shiny, and you can see a little bit of the silvery white kind of aspect to it. Their general reactivity, they are highly reactive as well, but they are not as reactive as the group 1 alkali metals. So these ones, while still highly reactive, are not as reactive as the group 1 metals. And again, similar to the other, similar to group 1, the reactivity increases as you go down. Again, for very similar reasons. So that means calcium is going to be more reactive than magnesium and beryllium. Their occurrence and extraction, they are all found in the Earth's crust, but they are not found in elemental form. So again, if we go back to those examples or those pictures of magnesium, of calcium, of beryllium, you're not going to find them in those general forms because they're, again, too reactive to actually exist in those forms naturally. But we can find them in the Earth's crust, and they're widely distributed in rock structures. So you will find them intertwined or combined with other elements, but you won't find them kind of free floating, and then you won't find a piece of calcium on the ground anywhere because, again, they're too reactive to exist in that state. The physical properties of the alkaline earth metals, they are harder and denser than group 1, and they have higher melting points. So again, while they're still similar, but they, in terms of metals, but they are harder and denser, and they have higher melting points. Looking at the Bohr-Rutherford diagrams for beryllium, magnesium, and calcium, again, we can see why they would be highly reactive. If you look at the electrons in the outer shell, there are only 2, which is a common trait for all group 2 elements, that you will only have 2 electrons in the outermost or the farthest shell, or the valence electrons that we've talked about before. So again, that's part of the reason of why they're highly reactive. It's easy to lose 2 electrons, right? You only have 2 of them out there. While it will take more energy than your group 1 elements, it's still not going to require that much energy to pull these 2 away. Again, that's why when we look at why calcium is more reactive than beryllium, again, you can think because those 2 outermost electrons are in the 4th shell, they're far away from that positive nucleus or that positive core. So the strength or the hold or the attraction between those 2 electrons and that center are going to be actually weaker in calcium than they would be in beryllium. So it's easier to pull those 2 electrons away, which is again why you get more reactive the farther you go down the group. Group 17 are halogens. So now we're moving all the way over to the right side. We're looking at the halogens in the 17th group. So fluorine, chlorine, bromine, iodine, and astatine. Again, we're only looking at the first 20 elements in total. So we're really focusing on fluorine and chlorine in this case. The appearance of the halogens, so these, while they share similar characteristics, their appearance or the appearance does vary between all of the elements in this group. So fluorine is a poisonous pale yellow gas. Fluorine is a poisonous pale green gas. Bromine is a toxic and caustic brown volatile liquid. And iodine is shiny, black, and solid. And when it sublimes, or it goes through sublimation, it turns into a violet vapor. So 4 different elements that we're looking at, and they all have various appearances, right? Whether it's a gas, a liquid, or a solid, and the colors as well, they all vary. So appearance is not one of their common traits. So looking at the halogens, we can see the fluorine, the chlorine, bromine in the liquid, iodine. You can see the 2 parts. You can see kind of that shiny black solid in the watch glass, and you can see the violet vapors coming off of it. So again, vastly different appearances between the halogens. Their general reactivity, they are a very similar set of elements, so this is more where the commonalities come into play, and they react violently or very violently with other elements. And again, we'll talk a little bit later in another note about why, and we'll look a little bit at more of that when we see the Bohr-Rutherford diagrams. But these halogens react very violently with other elements, and the reactivity decreases as you go down the group. So this is different from the alkali metals and the alkaline earth metals, where the reactivity increased as you went down. With the halogens, the reactivity decreases as you go down. So that means fluorine is more reactive than astatine. The occurrence and extraction, again, similar to the other elements that or the other groups that we talked about, the halogens are too reactive to occur in nature. So again, you can find them, but you're not going to find them. You're not going to find chlorine gas floating around. You're not going to find fluorine gas floating around just because they're too reactive to exist. They're too unstable. The physical properties, as you go down the group, the melting points and the boiling points increase. This kind of makes sense because as we go down, we go from a gas to a liquid to a solid in terms of fluorine, chlorine, bromine, and iodine. So which makes sense that if it's a liquid, that means the boiling point is going to be higher than if it's a gas in its natural state, right? So if it's a gas, it means that the boiling point is very low if it exists as a gas. Same with a solid compared to a liquid. A solid has a higher boiling point than a liquid because the liquid is already melted or turned into a liquid. So as you go down, the melting points and the boiling points increase. Looking at the Bohr-Rutherford diagrams, or a version of that, we look at fluorine, chlorine, and bromine. Looking at the outer shell, there are 7 electrons in the outer shell, which is again another commonality between the group 17 halogens. They will all have 7 electrons in their outer shell. Again, the electrons in the outer shell, we'll learn in a later note that you want to have a full electron shell. So in this case, they would want a total of 8 electrons in their outermost shell. Now, because they have 7, it's easy to gain 1. So if you're trying to add in another electron or add in a negative force, it's easy just to have to add 1 rather than 2 or 3 electrons. So that adds to the reactivity, similar to the alkali metals, where they were very reactive because they wanted to get rid of 1. Bohr-Rutherford, the halogens are very reactive because they only need to gain 1 to react. Again, reason for why they are more reactive as you go up the group. If you think of trying to attract negative forces or negative particles, the closer those negative particles are to that positive core, the stronger the attraction. So if you look at fluorine compared to bromine, the attractive forces between the electrons and that positive core in fluorine are going to be a lot higher than the electrons in bromine and the positive core. So that means the electrons are more likely, or there'll be stronger forces in fluorine compared to bromine. So they'll be more reactive in fluorine. Group 18 are noble gases, so helium, neon, argon, krypton, xenon, and radon. Again, we're only focusing on the first 20, so helium, neon, and argon are the main ones that we're concerned about. but because they're in a group, all of the characteristics are shared amongst these 6 elements. So the appearance kind of comes from the name, noble gases. All of these elements are gases. Looking at them here, so helium, neon, argon, krypton, xenon, just kind of a brief or a kind of a modified view of them. You're not going to see them appearing as these colors, right? We can see helium in balloons and stuff like that, where it doesn't really have a purple or an orangey color to it. However, when you do pass electricity through it, like kind of like a neon sign, they do produce different colors. So this is just another way of seeing it. This is not how they would normally appear in nature. Their general reactivity. Noble gases are generally considered unreactive. And again, we'll talk a bit more about that in another note, and we'll touch on it briefly. But they are unreactive. And this is because they have what is called a closed shell configuration. And again, we'll mention that again a little bit more briefly, but we'll go into more detail later on in another note. So in these noble gases, they form no known compounds. So that means that these noble gases just exist on their own. So you're not going to find a helium mixing around with another element. It's just going to be helium gas on its own. The occurrence and extraction. Noble gases are all found in minute quantities, it should be quantities, in the atmosphere. So that means they're all found naturally in the atmosphere, just in small amounts. And helium can sometimes be obtained from natural gas wells, which has just come from decaying radioactive material. That's one thing you may have heard about, like the price of helium, or the fact like balloons with helium cost a lot. Basically, helium is a non-renewable resource, so eventually we will run out of helium. But for right now, it's still available, but it is non-renewable. So the amount of helium that there is basically all that there will be. The physical properties of noble gases. They boil at low temperatures, which again explains why naturally they exist as gases. Because again, the boiling point is so low. And helium has the lowest boiling point of any substance. So looking at the noble gases in their Bohr-Rutherford diagrams, the reason why they're so non-reactive, we'll touch on this later. An element or an atom is reactive or becomes reactive or wants to react to basically get a full valence electron shell. So that outer shell, the atoms want to be full. The elements, they want that outer shell to be full. And in this case, all the outer shells of noble gases are always going to be full. Helium with 2, neon with 8, argon with 8, radon with 8, xenon with 8 in that outermost shell. So their outermost shell is always full. So it doesn't need to react with anything, or it doesn't want to react with anything. And lastly, hydrogen. Now, hydrogen is unique, and it's classified in its own group, despite where it's placed on the periodic table. So on a periodic table, it is the first element, and it does appear to look like it is in the top of group 1. However, hydrogen is not considered an alkali metal. It is in its own group. And that is because it doesn't fit any of the characteristics of the other alkali metals, but based on its electrons and its mass, it does need to be number 1. So the hydrogen's appearance, it's a clear and colorless gas. You can't hear it, or you can't see it. There's no color to it. Similar to the gas lab that we've done in class, you can produce it, but you can't see it compared to anything else. That's why we need to do the gas test to make sure that, or to identify what type of gas we have produced. So again, just a diagram of hydrogen. It's kind of hard to show a clear and colorless gas, but in general, if you've done the gas lab or identifying gases lab, you have seen hydrogen in person. The general reactivity of hydrogen, it is very reactive. And again, we'll look and touch on that briefly, but it is very reactive. It is extremely flammable, and it is responsible for one of the biggest things aside from like hydrogen bombs and so on. It is responsible for the Hindenburg explosion. So you may have seen this picture, but basically they had a giant blimp or dirigible or whatever you want to call it, and because hydrogen is so light and it's very buoyant, and it's not as dense as oxygen, so basically it floats. Basically they filled a blimp full of hydrogen, and they were using that to float in the air and propel itself and so on. However, it hit a tower, and I believe sparks ended up igniting the hydrogen. It reacted, and it caused the destruction or the explosion that you can see here. And so that's a big reason why a lot of blimps now use helium, because helium, as we just mentioned, is very non-reactive. So nothing like this will happen with helium. Occurrence and extraction. So hydrogen is the most abundant element in the universe. It makes up about 90% of the universe by weight. So it's in everything. It's in water. It's a large component of water. It's in everything. And if you're looking at the Earth's sun, it's the most abundant element on or in the Earth's sun. Part of that applies to why you can kind of see like the flames and the reactivity of the sunburst, right? It's just a hydrogen gas. Physical properties: it is the lightest element, which goes back to why they would have used it on the Hindenburg, because it is very light. It has a low melting and boiling point, which again explains why we see it existing as gas in its natural state. And finally, the Bohr-Rutherford diagram. So looking at this, again, there is only one electron in the outer shell. So if it wants to have a completely full, or if it wants to get rid of all the electrons, in this case, it can either gain one or it can lose one, so it can do one or the other. And so this makes it highly reactive. If you think about if you're losing an electron, and all you have is a positive charge, there's no other electrons there, or you gain one, or you're creating like or you're dealing with a very reactive atom. So that one electron in its outer shell does lead to the characteristic of it being highly reactive, very similar to the alkali metals in group 1. But again, that's just looking at the different families or the different chemical families in the periodic table. The alkali metals, the alkaline earth metals, the halogens, the noble gases, and hydrogen. Those are the main ones that we're going to be focusing on.